Hey guys, Mason with Digital Capital here. Today I'm going to be continuing my NEO series and I'm going to be talking about NEO's consensus algorithm. It's called Byzantine Fault Tolerance and I'm really excited to dig into how it works and show you guys a few different examples with it. Let's get started. So the NEO consensus algorithm of Byzantine fault tolerance is actually named after a problem called the Byzantine generals problem. So the problem arises when a group of Byzantine generals all surround a city and they have to reach a consensus as to whether they should attack or they should retreat. And the problem can be further complicated by the unknown presence of some traitorous generals. Let's say there are 7 generals and 3 of them want to attack while the other 3 want to retreat. If the 7th general was a traitorous general, he could send half of them attack votes, while selectively sending retreat votes to the other half. This is a huge problem because a haphazard attack could result in devastating results for the Byzantine army. In the NEO white paper, they're arguing that if you can get the consensus to 66.6%, or in other words, if 2/3 of all the generals agree, then you can actually eliminate the possibility of dishonest persuasion. So let's take a look at how the NEO network deals with a dishonest node being part of their consensus algorithm. And we'll do that by taking a look at a couple examples. When it comes time to add a new block to the NEO blockchain, one of the nodes is designated as the speaker, while the remainder of the nodes are designated as delegates. The speaker then proposes a new block to be added to the blockchain by sending a message to all of the delegates, and the delegates go ahead and relay this message to each other delegate. The entire data set during this consensus activity is referred to as the view. In this first example, things are relatively straightforward. The speaker is proposing an honest block, designated by the letter H here, and all of the delegates go ahead and relay the honest information. In this example, consensus would be achieved, and a new block would be added to the NEO blockchain. Let's switch up the view and take a look at this example, where we have one dishonest delegate. The honest speaker is sending honest data to both of the delegates, but the delegate on the left is receiving dishonest data from the dishonest delegate on the right. And the delegate on the left doesn't have a way to determine if it's the speaker who's dishonest or if it's the other delegate who's dishonest, because he doesn't have access to the data that the speaker is sending to the delegate on the right. In this situation, the speaker is only going to receive a prepared response, which is essentially just a node saying, hey, I agree with everything that's happening here and I want to add this block to the blockchain. The speaker is only going to receive that message from the delegate on the right, who's the dishonest guy. The delegate on the left is going to say, I'm getting 2 different sources of information, one from the speaker and one that I can't verify coming from the delegate on the right. So because I'm getting dishonest data, I'm not going to send a prepared response. This is going to result in the view being changed and the consensus algorithm starting over. It's worth noting that it doesn't really matter if the speaker is the dishonest one or if the delegate on the right is the dishonest one here, because either way, the node on the left is going to receive dishonest data and it's not going to send a prepared response. So let's look at another example. In this example, we have 2 honest delegates and 1 dishonest one. The speaker is also honest as well. So the honest speaker sends an honest block of information to each of the delegates, and the dishonest one goes ahead and changes it to dishonest information and passes that on to the other 2 delegates. Now, in this situation, which is slightly different from the last one, we have 2 delegates that are agreeing on the honest block of information. And so a 66.6% consensus has been achieved in this scenario, and the honest block of information will get pushed onto the blockchain. It's again worth noting that the 2 delegates who are achieving consensus have no way to determine if the speaker is being dishonest or if the other delegate is being dishonest. But like the last situation, it really doesn't matter who's being dishonest. The fact is that they're achieving consensus with honest information and the block is going to go ahead and be propagated onto the blockchain. Let's take a look at a final example, this time with a dishonest speaker. The speaker is sending honest data to one of the 3 delegates while sending dishonest data to the other 2. The 2 receiving dishonest data are going to reach a majority consensus that they'd like to change the view and no blocks will be added to the blockchain. In this example, if the speaker had sent honest data to 2 of the 3 delegates, they still would have achieved a majority consensus, but they would have added the block to the blockchain without the need for a view change. The most important thing for the system is that we don't append blocks without honest and validatable information. And you can see from these examples that in none of them will we ever add a block with dishonest data. There's a lot more that can be said about this consensus algorithm, from the variables that actually go into proving that it'll work, to Monte Carlo simulations that the NEO core team has run, showing how long it will take to achieve consensus based on how many honest and dishonest nodes there are. I'm not going to be digging into everything in this video, but I do want to go over some of the benefits to using the dBFT algorithm over something like proof of work, which is what Bitcoin uses right now. With dBFT, the consensus is actually happening before we add a block to the blockchain. And because of this, NEO has something called one block finality, which means that after a block is added to the blockchain, we know that that change is permanent, and there will never be a fork that reverses that change. Because dBFT isn't based on computers racing each other to try and solve a really complicated math problem, it's able to achieve much faster block times than the traditional proof of work based blockchains. The current block time for the NEO blockchain is on average 24.2 seconds right now. This faster block time, in combination with the fact that there's really minimal computer cycles that go into the dBFT algorithm, means that the energy consumption for NEO is much, much less than the energy consumption on Bitcoin. And finally, because that consensus is achieved before we add blocks to the blockchain, you're never going to see a fork of the NEO blockchain. So please be aware, if anybody is claiming to be a fork of the NEO blockchain, something maybe like a NEO Connect, NEO Gold, or NEO Cash, those are probably scams, and I just want to issue a word of caution to you guys. If you do see those around, please be very careful about investing in them. I hope you guys enjoyed this breakdown of the dBFT algorithm, and I hope that you learned something from it as well. If anything, I hope that it made you think about at least the different consensus algorithms that are out there and the positives and negatives to them. There are certainly some negatives to the dBFT algorithm, and I want to dig into criticisms on the NEO network in a future video. But I have a lot of other stuff I still want to talk about, and these videos take a while to produce. So be on the lookout for the next one. I'm probably going to be talking about a lot of the software that exists in the NEO ecosystem, from the different wallets you can use to a lot of different other exciting projects going on. So be sure to check in for part 3, and I'll see you guys next time.